Hello, my name is Jed Murdoch. Welcome to Module 5 on Source Sink Dynamics. In this module, we'll cover what a source is, what a sink is, what source sink dynamics are, and how you can model source sink dynamics to make some predictions about these systems into the future. So I'll run through a few of the basics, give you a bit of an overview here at the beginning, and then I'll pass you along to my colleague Terry, who will run through a spreadsheet exercise that will sort of show you the mechanics of how the things I'll talk about in a moment actually work. So to begin, I'd recommend, if you have a moment, to review the basic population growth model, because we'll use that model to develop our source sink model. In fact, we'll sort of build on it. We'll add in a couple of other components. So I'd recommend that you have a look at that one, review it before proceeding if you have a moment. So let's consider a population, right? A population is a group of individuals of the same species occurring in the same place, the same area at the same time. As population biologists, as conservation biologists, we're oftentimes concerned with the fate of a larger population. We may want to ensure that we have enough individuals in that population so that it's stable, it's persistent from one year to the next. Now, if you think about the individuals in a population, we know that some individuals will occupy really good habitats. So there may be particular habitats that are very good, and those individuals that occupy them actually have some benefits here. They tend to have higher reproductive output. They tend to have higher levels of fitness, let's say. And again, that's fitness in the biological sense, not the sort of physical sense, but biological meaning, increased survival and reproductive output. And in these, landscapes, we may also have individuals that are living in poorer quality habitats, so those habitats that aren't quite so good. And those individuals sometimes have lower reproductive output. It's a lower quality area, so their fitness may be diminished. To give perhaps a hypothetical example using one of my favorite species, African wild dogs, large canid that lives throughout Africa, perhaps 3,000 to 5,000 left in the wild. We may have wild dogs occupying nice woodland habitat, good stuff for wild dogs. Their reproductive output may be quite good. But then we may have wild dogs occupying more open plains as well, and those open plains are not as good. They're lower quality for these wild dogs because there are lots of competitors, there are lots of hyenas out there, there are also lots of lions in these open areas, and so there may be fitness consequences to those types of habitats. So the fate of a population, right, our concern as a population biologist, really depends on the sort of successes within our population that occur in these good habitats among individuals, and it depends to some extent on the losses or the reduced influences on individuals in poor quality habitats. So it's sort of this balancing act. And we call this sort of realm of population dynamics, right? Population dynamics that involves this sort of balance of good and bad habitats, source sink dynamics. So what is a source? Sources are typically these good habitats. So a good habitat that's a source habitat is one that has simply higher levels of birth than death. So a source habitat has more individuals being recruited or born into a system than are actually dying, which is a relatively simple concept, and I'm sure you can envision that perhaps with our wild dogs here. So think about that population, a source population and a source habitat, for example. What do you expect that population to look like over time? Certainly source populations, because they're producing all these extra individuals, are at a point at which they're continually growing, as you can imagine. So source populations, when they reach a carrying capacity, get to the point at which they've got to start chucking out individuals. They have to start exporting them elsewhere because there may not be enough space in that particular habitat. There's not enough food resources. There may be too much competition for foods and habitats and space and mates and all that good stuff. So they are sending out individuals. They're exporting individuals, and we'd probably refer to them as being net exporters. So we also have these poor quality habitats, and the poor quality habitats in some ways can be sink habitats and contain sink populations. Not always, but in some cases. So a sink population is kind of the opposite. A sink population is one that meets the criterion that there are fewer births relative to deaths. In other words, more individuals are dying than are being born. So think about how that plays out now at a population level. What would that sink population do if it was left to its own devices, if it was isolated from everywhere else? That sink population, rather, would essentially swirl down the drain of the sink to extinction because there are more deaths than births. So left to its own devices, a sink population would decline eventually to extinction unless it receives individuals from elsewhere. So these sink populations tend to be net importers of individuals. That's the only way that a sink population can continue to exist. So again, as conservation biologists or population managers, we're interested in ensuring perhaps the viability of a greater population. And if we see that we have a population existing in this source sink system in which we may have a subpopulation consisting of a source and another consisting of a sink, we may be able then to describe that system, to describe this sort of balancing act between sources and sinks through a modeling process. And if we can model, we can describe those dynamics, then we can get at what we expect the total population size to be, and not only at a specific time period, but we can project how that population size will change throughout time. So source sink systems sound pretty appealing. I think it's a relatively straightforward concept, but certainly source sinks don't apply to every species in every situation. But we have seen a number of studies that have shown that source sink systems are actually operating for a number of plants, a number of animals, both on land and in the sea as well. And perhaps to give you a real-world example, let's consider a population of another one of my favorites here, the key deer. Now the key deer, some of you might be familiar with this organism. The key deer is a subspecies of the white-tailed deer, and it's endemic to the islands of the Florida Keys, or the Keys, I suppose, of the Florida Keys. The key deer is sort of this miniaturized, it's a very small, miniature white-tailed deer. It stands maybe 30 inches high, probably weighs 50 to 60 pounds, really enduring creatures. So we know there's a good population of key deer that live in Big Pine Key, which is a good-sized key in the Florida Keys. Now, Big Pine Key went through a period in which there was a fair amount of residential and commercial development that occurred sort of in the middle part of this key. And that separated the population into two. So our key deer population was organized now in a northern population and a southern population. And so biologists spent a fair amount of time trying to develop ways to ensure the persistence of this larger population, and found that in the north we had the northern population existing as a source. So it met that criterion that in fact we had larger amounts of births, more births than we had deaths. And the southern population really seemed to be acting like a sink. There were more deaths than there were births. So we had this classic system here set up in which we had a source population and a sink population. So the source population was exporting individuals, and the southern population was importing individuals. So we had enough individuals leaving the source population that were trickling through, managing to get through these residential and commercial areas and reach the southern population. And enough of those individuals reached the southern population to offset this higher amount of births relative to deaths. So as a whole system, the whole greater population was relatively stable. There's a slight imbalance still in reality, but by and large, we see this source sink population, the source sink system operating. So how do we use a model to describe a source population and a sink population, and to make some generalizations about the population at large, or to perhaps chart dynamics over time? What we really need to know are some characteristics of our source population and to build a model just on our source, and some characteristics of our sink population and to build a model on our sink population. We then sort of combine those two models then to estimate the greater population at large. So let's cover how you'd go about modeling these two individual populations with a few basics about population modeling. We want to know how our source sink system changes over time, and in order to do that, we need to build separate models that capture that amount of change, right? So we need a model that describes, as I mentioned, our source, and a model that describes our sink. And we'll look at the interplay a little bit later between the two of them to see how that whole source sink system plays out. And we'll be interested in charting its dynamics over time, or what we expect that system to behave like over time. So in order to do that, we've got to build, again, these population models describing our source and sink populations. So I'm going to run through some of the main components of a population model. In order to estimate, again, how a population changes from one period to the next, what are those factors that we really should be considering? Well, there are four primary factors that are quite central to any population modeling. And those factors are typically referred to as the BIDE factors. And you might have heard these before, but the BIDE factors are really key to plotting how a population changes. What are they? Well, B represents, of course, the number of births. So those individuals that are born into a population will affect its number, right? What does I stand for? I stands for the number of immigrants. So these are individuals from elsewhere that join the population. They immigrate into it. That, of course, can also have an effect on a population size, as can the number of deaths, as well as the number of immigrants. And those are the individuals in the population that are leaving, they're exiting the population. So these are our primary BIDE characteristics. And with them, we can build a basic model that describes how that population changes. So this is that basic model. And it looks a little complicated, but it's actually really quite straightforward. All it's saying is that what we expect our population to be like in one time step into the future, or one time step away from wherever we're at, let's say at present. So NT here refers to our population size. We could call it at present, but it's really at time t. And let me just further define this here. Our NT plus 1 is our population size at time t plus 1, so one step ahead, like perhaps 1 year into the future. So that value is what we have now plus our number of births plus our number of immigrants, right? So we're adding these to the population minus the number of deaths minus the number of immigrants. Which sort of makes sense, right? So we've got our current population, we're adding here with these two terms and subtracting with these two terms, and that then should give us a value for what we expect the population to be like. So there's one more point I want to make here. With this model, we are assuming that time occurs in discrete units. So we're assuming that time is like years or seasons, and so we're projecting population changes from one discrete unit to the next. So time is not assumed to be continuous.